Good morning, everyone. My name is Han Hong-Dok. I'm a student of Professor Ziyong Kim from Songkyungwon University. Today, I would like to present the topic, Techno-economic and environmental analysis of CO2 utilization framework for liquid fuel and chemical products. Firstly, let's take a look on the industrial use of CO2. That's estimated for 2020 and 2030. There are a huge CO2 potential from a large resource emission, while there are only a small amount of CO2 have been industrially utilized. You can see here, even though there are high rates were estimated for sequestration and underground, and for the utilization for material, there still a large surplus of CO2 for energy-based products. So in this work, we develop and design the framework of CO2 captures and utilization for energy-based products called CCU4E. In this framework, we utilize several CO2 utilization technology like catalyst conversion, thermochemical energizing, electrochemical reduction, biological fission for various fuels. So this work includes several steps. Firstly, we identify the problem of the CCU4E, thus utilize several different conversion and renewable source. Then we develop the CCU4E superstructure, includes 72 pathways of CO2 to fuel. And then the process simulation was developed. The information further used for techno-economics and environmental analysis with UBC, that's unit production cost and net CO2 emission, NCE. The further extended sensitive analysis were performed for several different scenarios of the renewable source, conventional source, in different countries, in the current or the future perspective. CCU4E superstructure was developed by integrating several technology for diesel fuel. That includes 4 types of the compounds and several types of technology. Its pathway does continue from the CO2 utilization technology, and then a pressing process and separation for the purified product. The process simulation of each unit or the full pathway was performed using Aspen Plus. Here you can see in the table there's very briefly description for the units process. Is kind of conversion process, separation process, and pressing process here. The energy and mass balance, sizing, and cost data obtained from the simulation will use for the further analysis. As a result of the techno-economics and environmental analysis, the UBC and NCEs of 72 pathways is sold in the figures because the pathway different in CO2 utilization, different in target product, so they require different input of material and utility that result in diversity of UBC and NCE. As you can see here, the catalyst conversion is able to produce lower cost and lower emission for CO2-based fuel compared to the electrochemical reduction and thermoenergizing. Here is the breakdown of UBC and NCE, and this one is the markets for each product. You can see the CO2-based fuel is produced at higher price compared to the market price. So we need more effort to reduce the cost and reduce the emission of the fuel. The breakdown of UBC and NCE help us to identify which one is the key factor for that target. As stated before, the catalyst conversion technology is able to, it kind of economic pathway for its fuel, and it's identified as hydrogen price in the K factor is up to 75% of the UBC. So from this point, we mostly target for example the CCU4E with several scenarios of hydrogen, vary by country, vary by resource, and in the current and future status. There are trade-off between economics and environmental impact when we use green or black hydrogen. If we use green hydrogen, green is mean renewable hydrogen, that will produce fuel at extremely high, but is able to reduce a lot CO2 emission. Otherwise, when we use black hydrogen, it's cheaper for the fuel, but the environmental target cannot ensure. For example, in the FT fuel and DME, those are emit CO2. Also, during the framework, there are several pathways for X fuel. So we identify the optimal pathway for X fuel according to hydrogen price. As you can see here, there are several linear lines. It indicates that the fuel source produce. There are only one optimal pathway for fuel during the exam hydrogen price, but on angle one, for example, DME, the gray line here, it means that DME is better to produce with the pathway number 27 if hydrogen lower than $4.83 per kilogram. Otherwise, it's better with the pathway 28. So depending on the country resource, there are several scenarios and several decisions were made for using green or black hydrogen to utilize in the CCU framework. There are top 6 countries of shared CO2 emission is China, US, Europe, India, Japan, and Korea were examined in this study. For most countries, the olefin is kind of economical product compared to other with lower price, and they reduce CO2 emission. For China and India, the hydrogen, black and green hydrogen price, especially renewable hydrogen and renewable source, very plenty and very potential in China and India. So it's possible to produce lower CO2-based fuel, lower price, and of course they reduce CO2 emission. For US, hydrogen price of black and green are potentials in US, but especially is the black hydrogen price. Black hydrogen, because there are a lot of natural gas and shale gas that for hydrogen production. Otherwise, Korea and Japan is not recommend to implement CO2 utilization framework in this current status, because both green and black hydrogen is still expensive. That makes extremely expensive CO2-based fuel. So this work also provides several scenario and strategy for country to make their whether they use the black or green hydrogen to balance economic and environmental. Further, we also examine the green fuel price for the future from 2020 to 2030. As you can see, this one is the hydrogen price of green and black base, and this one for estimate for the CO2 based fuel. According to hydrogen price trend, The clean fuels is estimated to narrow down and cheaper in the future. It's mostly because the large effect of the hydrogen price. So it points out that there are very, very potential to utilize cleaner and cleaner hydrogen, renewable hydrogen to produce CO2-based fuel in the future. In conclusion, this work estimates 72 pathway CO2 to fuel product using various process system engineering stages like process simulations, optimization, techno-economic analysis, environmental performance. And this work also provides some strategies for countries to identify how to use their domestic hydrogen for the for CO2 utilization. This is all from me today. Thank you very much for listening.
Okay, thank you for your presentation. 네, 시간이 남아있는 관계로 질문이나 코멘트 입성에 받도록 하겠습니다.
Thank you for your comprehensive talk. I'm still a bit confused on page 6 what you meant about catalytic conversion being more, what was it, efficient or effective than thermochemical or electrochemical. But aren't all of those catalytic by definition?
Oh, sorry, you mean that you still confused for why the catalyst conversion is quite economical compared to the thermal and electrochemical reduction?
Yeah, I would like to know, or if you could clarify, what is the catalytic conversion and how is it different from thermochemical or electrochemical?
Okay, see.
Because you had a statement on page 6 where you explicitly.
Okay. For the catalyst conversion, our first material is CO2. So if for the first conversion of CO2 to any intermediate or product, it means if we use the catalyst for that conversion, it's called catalyst conversion. But in the thermochemical enzyme, we use the concentrated solar heat to break the chemical bond of CO2 to intermediate like CO, the monocarbon. And for the electrochemical reduction, it's use electrolysis to convert CO2 to any other type of fuel.
Okay.
Yeah.
The thermochemical is the solar-driven conversion.
Yeah.
And
The thermochemical enzyme is still high because they're especially in the capital cost of equipment. This one.
Okay. Yeah,
Yeah.
that's clear. Thank you.
혹시 또 질문이나 코멘트 없으신가요? So I wonder if you apply the same capital cost, for example, for electrolyzer for each country, or is it different for each country?
For each country, I will show you with the figures. For example, if we assume that there are the same amount of energy fuel and the same pathway, for example, this pathway for each country is really different in terms of the hydrogen cost and utility cost. It's also different in the CO2 factor for each country, so that affects the final result. Thank you very much.
Yeah, thank you for your nice presentation. 박수 한번 부탁드립니다.